Time this case.
Yeah. Hello, everyone. This is lecture 29 of Petroleum Reservoir Geomechanics 465-531. Today is an important lecture. We are going to do a very important, we are going to revisit an old topic from Module 1, which is the orientation of Mode 1 fractures. We did it for, in the Module 1, if you remember in the exam as well, we did it for SV, SH max, SH min. And basically, those considerations that we saw ignore the influence, any effects from the presence of the wellbore. Now that we have seen, okay, what is the presence of the wellbore is doing, how does it affect the stresses, we are going to do the same considerations for considering the impacts from the wellbore. So, oh yeah, last time there was somebody who knocked the door before I thought it was a class coming in, but it wasn't a class coming in. So I rushed to finish the class. But yeah, I did something very quickly, so I want to redo it to make sure that you guys understand it well. So we talked about the near wellbore stresses. We said, let's start from here. Okay. So when you drill a wellbore, you interfere with the surrounding stress field. So the stresses in the near wellbore vicinity, they are not basically the in situ stresses that we talked about earlier, SV, SH max, SH min. You now have a new set of stresses that are in cylindrical coordinates. You have the radial stress with green, the tangential stress, also known as the hook stress, sigma theta theta, the axial stress, and sigma ZZ, and the shear stress, sigma R theta. Now, I showed you how to draw their directions. It's the directions that I drew, the nodal directions. I don't care so much about the arrow direction. I care about the configuration. What I showed last time, and we show it also on this slide. The configuration of the stresses is very important. And I want you to know it for the exams coming up. To know the direction, where is sigma RR, where is the axial stress facing is.
And we said that sigma R is
Yeah, I don't care so much about the arrow direction because it will be dictated by you. I care about the configuration of the stresses. That's why I have this, and it's a shame that all the students are online, except Hakim, who's a guest. I have this, and Hakim knows about this. Basically, it shows the configuration of the stresses on the cylinder, which is the wellbore. Let's see, where is the camera? Why is the camera off? Okay. Oops, sorry. Somebody turned the camera. Yeah, that camera, the screen is okay, but sorry. They don't have a picture of me presenting for some reason. This camera is off. Oh.
No, it's working.
It's not working.
No, it will be working. It will be working. Just it's taking time.
Oh.
No, it's on.
Oh, there you go. There you go. We got it. I don't know who messed it up. The class before, probably.
Let's zoom in a little bit in because.
Yeah. I mean, I don't care about this camera too much because, yes, yeah, awesome. Thank you, Hakim. So this thing is like the paper towel, what it says, after you finish the paper towel, and then draw arrows with the proper colors. And, well, I guess if you zoom in, they will, know. But anyway, the office hours, the camera is, I take my office hours in the office so I can show you easier. It's good to have this. I even when I was many times when I was a student, I was going to conferences to present. I was taking it with me. Even when I went to for an interview for a position, I brought it with me as well. And I forgot to explain to them what was it for. So I must have looked weird walking around with it. Anyway, but I want you to know the configuration of the stress. Like basically, okay, the radial is in the direction of a radius going out to the circumference. If you extend that, that's the radial stress. Orthogonal to it, we get the tangential stress and the z stress along the direction of the well. And it's important, those directions, because they dictate fracture initiation. Now, before we get to that, I want to revisit the equations that we said earlier. And then we were talking about if you move far away from the well, it eventually becomes what are the in situ stresses. And we had an example on the top about theta equals 0, and an example at the bottom for theta equals 90. So at theta equals 90, the tangential stress becomes eventually equal to the SH sigma H max. The radial stress equals to sigma H mean, and the axial stress equal to sigma V. Now, I was drawing a schematic when that guy knocked the door, and basically it was, this is the well, this is SH max, SH max, SH mean, SH max, SH mean. Okay, this is the well. This is 90 degrees, right? 90 degrees. And I want the stress field here. Okay. So radial stress in this direction. Hoop stress or the tangential stress in this direction. Ignore the arrows where they are pointing. It shows tensile. Doesn't matter. It will be the other way around, but I'm just trying to make a nice picture. Axial stress into the plane of the screen. And look, the radial stress arrow is exactly parallel to SH mean, right?
Yes.
And the tangential stress arrow is exactly parallel to the SH max. That's how you understand it. And of course, the SV and the axial are also parallel. So that's what I was trying to show when the guy knocked the door. And then he told us that it was just looking to show a tour class.
Yeah, it was a visit.
Yeah, it was a visit. So anyway, so that's what I was trying to show. As you move away from the wellbore, eventually you go down to the in situ stresses. There is some confusion that I have seen. Actually, I would say from graduate students even, that they didn't understand that they thought of the stresses as two separate stresses. You had SV, SH max, SH mean, and you also had sigma Z, Z, sigma R, sigma theta, theta. No, it's not. They are not the same different sets of stresses. It's like that can exist at the same time. It's just when you get close to the wellbore, the stress field changes in a way that is better described by those stresses. But obviously, you can use the cylindrical stress field, cylindrical coordinate system to describe the stresses far away from the well, but it doesn't make sense. Okay, it doesn't. It would be weird values. Same thing if you are near the wellbore, you can use Cartesian coordinates to describe the stress field, but it's going to be again very weird values, very weird expressions. it just makes sense to go from Cartesian to cylindrical as you get closer to the well. And this is what modelers are doing. People who are using Flux 3D, if you are near the wellbore, you are using a radial system. And if you are far away from wellbore, you are using Cartesian system. And there is a way you can blend the two together. Okay, so now this is a very important thing, which is about the same problem that we did in the module one, about how do fractures initiate, right? We said the fracture will always open parallel to the smallness of the stress, sigma 3, right? And then you have, this is the width in the direction of sigma 3. And then you have sigma 2, sigma 1. Okay, the smaller of the two directions of the plane will be sigma 1. The biggest of the two will be sigma 2. And it was very, very sort of, it was confusing, but it became clearer and clearer as we went by. Now, I want to do the same thing for the stresses, the near wellbore stresses, okay? I want you to think of sigma RR, sigma theta theta, sigma ZZ, okay? So we will see now tensile fractures during stimulation treatments open by doing work against the least compressive in situ principal stress. That's not the first time you have seen this bullet point in this class. Nature's tendency is to follow the path of least amount of energy. Again, it's not the first time you see this bullet point. No reason to push away rock in a direction of higher stress if there is another direction in which stress is lower and it is easier to push, okay? Therefore, tensile fractures will be perpendicular to the least principal stress as long as S3 is the least compressive than S1 and S2. And by definition, this S3 or sigma 3 would be less compressive. By the way, sigma 3 and S3, they are basically the same thing in this case. They are pointing in the same direction. It's just that one has the impact of pore pressure in it. It doesn't change the fact that it's the least compressive. That's why sometimes you see it written as sigma 3, sometimes you see it written as S3. It really means the same thing. Okay. So in a purely triaxially loaded stress environment, a tensile mode 1 fracture opens in the direction of S3 and propagates in the plane of S1 and S2. Okay. That's why horizontal wells are drilled parallel to SH mean. Presence of wellbore and perforations can impact the stress state in their proximity. Again, it's not the first time you have seen this. You have seen this bullet points. But let's draw something that we did draw the last time. Okay. We have a wellbore like this in shale, and I want to draw the stresses on the edge of the wellbore, okay? I want the stresses let's first draw the stresses on the top of the well, okay? So this is basically like this. I'm looking at it from above, okay? In which direction it would be the radial stress? Yeah, so the radius of the cylinder. Sorry. Yeah. So it would be, if I go to the middle of the well and I put let's do it this way. This is the cross section of the well. I go in the middle of the well. I draw a line towards the edge, the circumference of the well, and I extend the line with a green arrow. This is the radial stress, right? Sigma RR. So in this case, it would be like this, right? Sigma RR. What about the tangential stress?
It is like.
Oh, that's correct. The way I drew it.
Yeah, but the direction is down.
Yeah, if it's compressive.
Yeah.
I'm drawing it as a tension so that the arrows don't intermingle, but yeah, obviously it would be compressive. Yeah. So the tangential would be like this, right? Okay. Sigma theta theta. Here I will draw it with a dot because it's coming out towards. Okay. What about the axial stress? It's along the length of the lateral. So it will be like this. And here it would be like this. Right? Okay. Now, I have a question for you. What kind of fractures do we like from a horizontal well? What did we like to get? Remember, I used the blue and red in the module 1.
We like to have the one that is perpendicular to sigma.
Okay.
To sigma ZZ.
Yeah, but
It's on the plane of sigma RR sigma theta.
yeah, that's exactly. But what's the name of those fractures? That's where I'm getting towards.
It's
Transverse.
transverse.
Okay. So I want fractures like this, right? Now a fracture like this, and normally I use blue to denote them, but now I'm using red to using black to avoid confusion. Look at how this fracture opens against the axial stress, opens against the blue axial stress. So it's basically a fracture like this, right? So it opens against the axial stress. So to get transverse fracture, from a well bore radius, let's just write it here. Transverse fractures open against sigma ZZ. Okay. So this transverse fracture, it's basically opening by doing work against the blue axial stress and propagating the plane of sigma RR and sigma theta theta, like Hakim said. Okay, so just like we did in the exam where we had we open against SH mean or SV, and we propagate in the direction of SH max and SV, propagating the plane between SH max and SV. Therefore, we have normal faulting or strike slip faulting, and in the first question, similarly here. Now I do incorporate the presence of the well bore. And now I'm saying, okay, I'm opening against sigma ZZ to get transverse fracture. So my sigma 3 or my S3 is the axial stress. Now, let's go back. And now let's try to produce something I don't want to see in the oil field for these wells, but I want to make a longitudinal fracture, okay? Normally, I color these fractures red, yeah. Okay, how does that fracture open? This fracture is like this.
Yeah.
How does it open?
It opens against sigma theta theta and
Exactly.
propagates towards the plane of sigma RR sigma.
Exactly. So longitudinal fractures open against sigma theta theta. And we said transverse fractures. Let me write it again. I wrote it before. Excuse me. What am I doing? Transverse fractures. And by fractures, I mean mode 1 hydraulic fractures, let's say, open against sigma ZZ. So let me paraphrase that. For longitudinal fractures, sigma theta theta is the sigma 3. For transverse fractures, sigma ZZ is sigma 3, right? So I can come here and say sigma 3, and I can come here and say sigma 3. Okay. Bonus point. What will happen if sigma 3 is the radial stress? Oh, sorry.
Yeah, pancake.
No. We can talk about the pancake, but I'm talking now from the top of the well. If the sigma RR is the sigma 3, I get something that basically is like this and then peels off, like the bonding. I get my triangles forming. I basically get, imagine I have a surface on top of the well that like not exfoliates, like peels off, like this peeling off. So I create separation between my cement and the well and the casing, basically. I create, let me draw it with black. Normally, I will draw it with green if I was writing a paper about it or something. But basically, this part here, like debonding, like, or let's make it like this part peeling off.
Yeah, actually, because it's not there.
Yeah, it's lifting it up. It's lifting it up while the well is.
For all the data.
Yeah.
It's a kind of circular failure.
Yeah, it comes out. So
it's like sleep.
Yeah, so people doing research on well integrity, and they care about debonding, the cement not being well. That's sigma RR corresponds to that. It's the same kind of failure. It's tensile failure. It's when sigma RR becomes sigma 3. And then when it exceeds the minus T, that's when it goes off. So now let's draw the stresses. This was on the top of the well, right? So, oops, sorry. Now I want to draw the stresses on the side of the well. I have this well, this is my cross section. So on the side of the well, I draw a radius to the walls of the wellbore, and I extend it. Sorry. I extend it. By the way, it's recording and it's okay. Yeah, it is recording. Everything is okay. We are sharing the right screen. I extend it. This is my radial. So on this, on the well, it's gonna look like, look at where the mouse is here. Coming out towards me, right? Out of the screen towards the audience, right? Coming out sort of there. What about the tangential stress? It's in this direction. So here it will look like this. And how is the axial gonna be? Same way, here is along the well. So always like this. Axial is very easy to get. When you get a well, see which direction is the well. Okay, this direction is the axial. Just bear in mind the well may not be the z-axis direction of the z-axis. It might be the direction of the x-axis. It might be the direction of the y-axis. So you may not call the axial stress sigma zz. You may call it sigma xx. You may call it sigma yy. You may call it sigma ii, where I can be variable. But as long as it's a normal stress with the subscript the same letter for the subscript, you are good. Okay, so let's go back to where we were before. I want transverse fractures from this location. What stress am I working against? Now, I want fractures like this. What stress am I working against?
To operate, I have to work against sigma z.
Yeah.
Sigma yy or x.
Yeah,
The blue one.
the blue one. Again, okay. Now, what if I want longitudinal fractures? It's hypothetically, I don't want longitudinal fractures, but say I got longitudinal fracture, how is it gonna look like? It's gonna look like a pancake that Hakim mentioned earlier, like this. The fracture is basically like this, or like this. What stress did it work against? Yeah, it worked against theta theta. Now you understand why I always use blue for the axial stress, I always use red for the tangential stress, because they are always the ones that are inducing longitudinal fracture or transverse fracture. It doesn't change if you change the angle on the wellbore cross section. And again, if you want the bonding, you have to do sigma RR. Like you have to go against sigma RR. So the bonding would be, imagine this is like this. And I want to fill the page of the well. So I'm basically, the bonding. I want to push it down. So I'm working with sigma RR. I'm pushing it out, pushing it out. It's a tensile failure again. Very nice. So what you learn how to do with SV, SH max, SH min, you now can do with sigma RR, sigma theta theta, sigma ZZ. Same thing, same problems, because it's the same principle. The tensile fraction will always open against S3, and it will always propagate in the direction of S1 and S2, more in the direction of S2 than in the direction of S1. But what is S2? What is S3? What is S1 can vary. In the first exam, and in the first module, we said it's SV, SH max, SH min. Now we are saying is sigma RR, sigma ZZ, sigma theta theta. So the same problems can be reworked basically to account for the presence of the wellbore. And this is what King Hubbard did. The impact of near wellbore stress interference on hydraulic fracture initiation. So for that, big implications from the interference due to the presence of the wellbore. Yeah, that's true. Several people say that, okay, to get transverse fractures, I just need to drill my wellbore parallel to SH min. If I drill my wellbore parallel to SH min, I'm gonna guarantee myself transverse fractures. And it's such a strong rule of thumb that in Louisiana is a state law. You drill your lateral north to south, your horizontal lateral north to south, and this is the direction of SH min in that area. It's towards the Gulf of Mexico. So everybody knows it. And the idea is that, okay, if I drill my well parallel to SH min, I guarantee myself I'm gonna get transverse fracture. The answer is no, not always. Not always, because the presence of the wellbore itself interferes with the stress field surrounding it, So where the fracture initiates, it's the fracture will start from the base of from the radius of the wellbore, right? Okay, that's where I'm looking at the stresses. The stresses at the wellbore radius is not as V as H max as H min. It's sigma R, sigma theta, theta, sigma Z, Z. So this is what I should be looking at. So my well may be drilled favorably, but I may not get transverse fracture initiation. And this is what my colleague Onomidis and Valko showed in their excellent book from 1995, Hydraulic Fracture Mechanics. They were, Valko was Economidis' postdoc, I believe, in Austria. Economidis was the chair of the department there. And I don't think he was his student, it was his postdoc. And he was a very mathematical guy who developed the continuum damage model for modeling hydraulic fracture propagation. And when Michael Economidis moved to Texas A&M, he brought him with him, and they became both professors in Texas A&M. Something like that. But I think Economidis went from Austria to Venezuela and then to Houston. So anyway, but somehow they got, they wrote this book in 95, and this was excellent book. It's very applied. If you're a petroleum engineer, this book will help you more than the book of Zoback, because the Zoback book is more of a, it has some theoretical aspects, and it's not just for near wellbore stuff. These are petroleum engineers, so they wrote only the stuff that matters for hydraulic fracturing. So it's a very, very nice book. Mark McClure was teaching a class in Texas, an elective course on hydraulic fracture modeling or hydraulic fracture design, and this is the book he was using. Very nice book. Actually, we will use this book in the next class. But yeah, so this is what they demonstrate here. You drill the wellbore correctly, parallel to SH mean, and you expect something like the top picture. Here, look at that. Transverse fracture, beautiful transverse fracture, beautiful transverse fracture, beautiful transverse fracture. But then you end up having something like in the bottom. So in the near wellbore vicinity, you got unfavorable fracture initiation, longitudinal, we use red, and then you move away from the wellbore. What happens? As you move away from the wellbore, the presence of the wellbore and its interference on the stress state diminishes, right? And you move back to the in situ stresses. Now you still have SV, SH max, SH min, and the wellbore is drilled correctly, so eventually it twists to become transverse. So if you take a microseismic measurement and you you try to look at the fracture far away from the wellbore, it's gonna be okay. But if you look near the wellbore, you are gonna find a lot of what they call near wellbore fracture tortuosity, which is a very bad thing. Basically, it's a lot of stuff, negative stuff happen because of near wellbore fracture tortuosity. You have something that in well completions or in hydraulic fracturing we call screen out, and that is when you are trying to pump proppant, it gets stuck into this constriction, twisty parts. And proppant is basically sand, and it cannot move anymore. And the pressure goes up. And the pressure goes up on the surface, but it doesn't, you keep pumping on the surface, it doesn't translate to a pressure increase down here. So you get the pressure on the surface to be roofing, but not down hole. Very bad thing. We call that a screen out. If you get a screen out, 70% or 60% pumping is over for that stage. Forget about it anymore. You're not gonna propagate any more fractures in that stage. Move on to the next. There are things you can do to mitigate that. It's better to try to prevent it than mitigating it after it happens or suppressing it. But yeah, early screen out is a bad idea. Also, remember those longitudinal fracture components, they can go long, okay? They can go long along the wellbore. And remember, you have a well like this, okay? And you try to stimulate it, and you are gonna do it in stages. This is the first stage you are gonna try to stimulate, and then another stage, and then another stage, and so on and so forth. Okay. Now, if I do what I have here, basically I get a transverse fracture far away from the well. Okay? Yeah. But in the well, and this is blue, is transverse, is coming out towards me, out of the screen. But the longitudinal components can be pretty wide, right? It can very easily extend beyond the length of the stage into another stage. By the way, when we say I'm stimulating in stages, I isolate the stage, the part of the wellbore I want to stimulate with packers, and then I pump fluid, so only goes through those perforations. Okay, if I get these longitudinal components extending beyond the stage, it means I'm getting fluid, fracturing fluid going to another stage. So I create inefficiencies. I don't create the fractures that I expect to create here. And then I have a stimulated well that is not producing as much as my model is saying is predicting it to produce. And I have a discrepancy. And then I have to reconciliate this discrepancy. And this is because this is what Valco and Economides propose. I get this. I was with my old advisor in Texas. I was talking to a lady from, at the time, she was with, I forgot what company was it, Swift? No, Southwest. And I'm not going to say her name, but I'm not going to say anything bad about her, of course. She was explaining some issues that they had. And it sounded like the reasoning behind those issues was stage communication. Fluid from one stage, I'm pumping to stimulate stage one. And then I'm getting problems because fluid goes into stage two, stage three, etc., etc. It sounded a lot like it was something like this. And then in 2015, there was a paper published by Jennifer Miskimins, who's now the chair of the Colorado School of Mines. She's teaching this class in Colorado School of Mines. They call it, I think, 361 or so. No, sorry. She teaches the next class, the stimulation class in Colorado School of Mines. They call it 361, I think. And she has a paper from 2015 that they use tracers in the fracturing fluid. So they knew, okay, this fluid with this tracer, we use it to stimulate stage one. This fluid with this different tracer, we use it to stimulate stage two, stage three, etc., etc. And then they did a diagnostic, and they found fluid from stage one into stage three, and fluid from stage two into stage three, and fluid from stage three into stage two and stage one. And they had a beautiful schematic that used different color for each fluid, and it shows them communication. It was very bad. And it explains early screen outs and poor productivity of a stimulated well. Okay, how much time do we have? 5 minutes, okay. So now what I described today, we'll start doing it mathematically, okay? How do I predict what orientation my fracture initiation will have? Just like in the first module, we said, okay, I have this SH mean, I have this SH max, these are their numeric values, 800, 700, 1000, and now tell me what direction the fracture will initiate. Okay, it's a little bit easier problem. You just look at the stress and you tell me which one is sigma 3. Now, it's still an easy problem, but you need to do a little bit more calculations. You need to take the equations that we mentioned before and set them R equals RW. What this will do, it will tell us the values of those stresses on the wellbore radius. So on the walls of the well, okay? And that will simplify them. Sigma RR would become basically just PW minus PP. Sigma theta theta becomes this. And sigma ZZ becomes this.
Sigma RW.
RW.
Sigma RW.
Where did I write that?
No, instead of sigma RR.
Oh, yeah.
Like when you take it literally, that R equal to RW.
Yeah, R equals to RW. And obviously shear stress is 0. But we knew that. Okay. Now, remember what we said is the tensile failure criterion in module 3. We spent most of the time talking about the more Coulomb shear failure criterion, which was this equation S1 minus PP.
Over S3 minus PP.
Yeah, that's for shear failure.
Less than equal than B.
Yeah, the right-hand side.
Yes.
What about the tensile failure? I did mention a criterion when we went.
So I feel we like we have a
I will write it.
sigma RR is going to T or
Tensile failure criterion sigma 3 less than minus T, right? Okay. Okay. So how do I incorporate that mathematically? Somebody tells me, Hakim, I drew the well. I have this vertical well. I'm drilling this vertical well, and I want to get longitudinal fractures from the vertical well because that's what I want from a vertical well. So I want fractures like this.
Mm-hmm.
I want you to calculate me what wellbore pressure I'm expecting these fractures. I should be expecting those fractures. So I know how many tracks to bring on location.
Okay, so for that mode of fracture, I have to determine what is my sigma 3 first.
Yeah, but I know it's longitudinal.
So since it's a longitudinal, then it's going to be the red one.
Okay.
So it's sigma theta theta minus sigma 3. And
Okay.
then I take the equation of sigma theta theta less than minus T and I solve.
Yeah.
Yeah.
Solve for what?
I solve for
What are you looking for? How high? What's the pressure at which the fracture?
so I solve for pressure PW.
No, for pressure or PW?
I solve for PW because
Yeah, excellent.
in drilling I solve for PW.
Yeah.
I change the PW.
Yeah, exactly. Yeah, you don't control PP. I assume that you know PP.
Yeah.
Excellent. Exactly what Hakim said. So to put it into analysis, what he said is that, okay, I have a vertical well. Sorry. Okay, I will fix it.
Sometimes if your pore pressure is changing too.
Yeah, but that would be, I assume that I know the pore pressure. Even if it's changing, let's assume I know it. Okay, I have a vertical well. And because it's a vertical well, I'm not gonna try to draw, we are old school. We drill the vertical well and we want to stimulate it with a longitudinal fraction. It's a fraction like this, right? And on the other side as well, like this. So it's opening against sigma theta theta. So Hakim said, take this equation, set it equals to minus t, because you know that this equation in this is basically sigma 3. Okay, now set it equals to minus t, and then solve for PW. Solve for this. So we are going to have something like PW equals, yeah, SH max plus SH min minus 2 SH max minus SH min cos 2 theta minus P plus T, right? Did I make a mistake? Okay. And assume I know all the values now. It's entirely theoretical, conceptual problem I'm giving you. Yeah. Okay, I got it. You did a Brazilian test in the lab. You told me it's 1,000 PSI, 800 something. T, I put it in. You told me how much SH max is. You told me how much SH min is. Blah, 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 blah. Good. Okay. Now, what about, I tell Hakim, I'm worried I'm going to have debonding in my well. So it's a well that is, it's a vertical well, and I have a cement, and I'm wondering if the cement layer around the well is gonna peel off. And then I'm telling him, this is my tension. Can you tell me what is the pressure at which it might peel off? What are you gonna do?
There is no sigma RR.
Yeah,
PW equal minus T minus P.
exactly. So what he said, which was 100% right, you come here, you take this. This is your sigma 3 now. You say it equals to minus t, and you solve for PW, and this is going to be a very easy problem. Minus t plus pp, something like that.
Yeah.
Yeah. Okay, excellent. Excellent. Now, though, I have the same vertical well, and I'm a stupid completion engineer, or I'm very shallow. I have diatomite on top, and I know I'm gonna get transverse fracture, so I cannot fight it. I know it's not a good idea, but I'm gonna get a fracture like this. Okay. And I'm asking Hakim, how are you gonna calculate, what's the Weber pressure at which I should be expecting transverse fracture?
No level pressure.
No Weber pressure, or I cannot find a Weber pressure?
No, because sigma is not the.
Yeah, I don't know. It could be an answer. I don't know. Not you don't know. I mean, I don't know. Like I cannot calculate it. I don't know because he's gonna come and take the.
We'll try and solve and then.
Yeah,
PW.
we cannot know. I guess is the right answer. So sigma 3, I said that equals to minus t, but where is the PW to solve for? There is no PW to solve for. And that's because of reasons inherent to the derivation of these equations. They do not have the plane strain theory of linear elasticity that we are doing for, that assumes a very long well bore, and the strain in the z direction basically is 0. That's why we don't have any well bore pressure in this equation. So now I'm a little bit of unlucky. So what do people do is that because they never want, but this is all the fractions they want in the horizontal well, right? In a horizontal well.
On a horizontal, yes.
Yeah, similarly, in a horizontal well, it would be a similar situation. He would probably give me this. He would probably use longitudinal and give me a value for longitudinal, but it can be very different, you know? So, or he can apply a more complicated model that does have sigma ZZ as a function of PW, and then you can do whatever you want, basically. You can do the same process. So that's the mathematical application of the analytical criterion. Okay, next time we're going to talk about the horizontal well, but I want to ask you something before I leave. We have 3 more minutes. Well, we are over time, but who cares? 3 more minutes. Just one question. Food for thought. Okay, this is how I'm looking at the well from above. And we said this is theta equals 0. This is theta equals 90, right? Okay. I can have fractions either starting from theta equals 0, theta equals 90, or anywhere in between, right? So how do I incorporate that in my calculations?
I may solve for a graph that has theta in the axis, and then see what's my.
Yeah, you can put it the value that you want here.
Yeah, I can solve for PW as a function of theta.
But it's a vertical well, so a vertical well will have at theta equals 0, I think it's SH max.
Yes.
Theta equals, by the way, I have another SH max, SH mean here. So at theta equals 0 is SH max. At theta equals 90 is SH mean. Now, always SH max is bigger than SH mean.
Yes.
Good. So what will be my theta for tensile fractions always from a vertical well?
Theta?
Yeah. Can I have for tensile fractions at theta equals 90?
No,
Yeah.
it's only for 0 degree.
Yeah.
Because that's the minimum.
Yeah.
Even I
Because,
think if you solve for PW as a function of theta, then you find that the minimum PW is for theta equals 0.
yeah, that's correct. That's correct. Yeah. So don't expect to get fractions starting from here. You will learn in this module something else that happens in this direction, the direction of SH mean. But what happens in the direction? The tensile fractions will always initiate. Let me just show you now before we finish, like this, right? Right? Okay. So these are my longitudinal fractions. And if I do sigma theta theta, what Hakim said is if I plug in here theta equals 0 or end theta equals 90, the theta equals 90 will yield a higher sigma theta theta at theta equals 90 is higher or higher than sigma theta theta at theta equals 0. That's what he's saying.
Means that theta equals 0 is less resistive.
Yeah.
It's like the easiest way to go.
Yeah. So remember, what I'm trying to do is this: sigma theta theta to be less than minus t. Minus t is a value, like minus 1,000. If I get it at theta equals 90, it means I already got it at theta equals 0, right?
Yes.
So that's why there is an answer to this. Okay. And with that, thank you very much. It's 3:30. I will see you on Friday. Yeah, homeworks are due on Friday, 11:59. Let me know if you have any questions. Email me, email the TA, and yeah, make sure you do it. This is a very important homework ahead of the exam number 2. It's the only homework that we have between the exams. Thank you very much. Have a nice rest of your